Good afternoon, everyone. This is a demo for the OpenCog NLP pipeline. So first, the general goal of the OpenCog NLP is trying to pass the sentence into some logic formalization, so we can inference language with other perception knowledge, including some common sense that has been stored in the OpenCog atom space. So first of all, for the natural language, we have to do some syntactic parsing, which we are using the link parser. To download the link parser, you can just Google search link grammar, then get to the episode. Yes, so if you want to try the link grammar, there are two versions, but the first link is very out of date, so probably you should try the second one. That's from the episodes. The link parser is just the pure C base. It's very easy.
What's the gain back there?
That was plugged in.
Oh, I see. That's.
Okay, I forgot. And also we have some like a partial semantic system which called RelEx, which integrate the link parser and to generate some syntactical semantic relation, which you can download from GitHub. It's on the sub project of OpenCog, so you can download. For installing the RelEx, we also have a wiki page. And yeah, there's a lot of instructions of how to install the RelEx. Then after the syntactic relation, then we have a bunch of rules. We call that RelEx.
I think maybe you can use that microphone.
Doesn't that work?
Well, it worked this morning. I think you just have to plug it in somewhere.
It's not just plugging it in. There's some switch to it.
Okay, yeah, but
I guess we can go.
But if she's not moving around, she can just use that one, right?
Yes. If we can figure out how to use that one. But that one's that's not one. You can go grab the.
There are a lot of pretty detailed instructions of how to install the RelEx. So anyone who is interested could try, and if you have a problem, we can discuss. Now I'm going to show some demo about the link parser and the RelEx. To run RelEx has integrated the link parser, so it can output the link parser as well. So to run the RelEx from the terminal, there's a file called relation extractor. So if you want to text some sentence, you probably need to edit the command line and put the sentence as an argument. So here is an example. The beautiful woman software case is a yellow ugly frog, then just very easy to run the relation extractor. Okay, so here we got a bunch of so this sentence has two parsers. As link parser only give like a syntactical legal like every possibility.
I will go hunt for the official AV guy.
Yeah, I couldn't
Knows how
find
this
it.
room functions.
Yeah, the link parser doesn't do any disambiguation, so it can generate all possibility of all part of the parts. So here. This is an English. Yeah. So for the first part, there's a link between basically the link parser output is all the syntactical relation between different two words. And so here, like for example, beautiful and woman, it has an ending which means adjective modifier. And the SS link, it means like subject and verb of subject. And then here is also like yellow is an adjective modifier for frog and ugly as well. Then we also generate a bunch of syntactical semantic RelEx output.
Please wait for a moment, it's really painful on the ears.
Testing.
Can you hear her? Yeah, that's good.
Yes, so it will generate object, which means the frog is the object of the case. And the software is the adverb modifier of case. Then woman is the subject of case. Then bunch of adjective modifier, yellow frog, ugly frog. And also we still keep all the syntactical properties of each word. Like for this example, the case is a present tense, so we keep that. Then keep all the part of speech. Case is a verb.
Hold on a moment. If there is a French speaker with a phone, I have a number for someone to call. They're going to the office. Anyone speak French?
Yeah, I'll try it.
What? Is it working on it?
Yeah.
Then I'll try it. I'll try it again.
Yeah, that was the number of the guy who set the thing up. This? That appears to be lights only, yeah.
Ben, the control room up there is open. There's a finite number of volume knobs.
Yeah. Well, sure. Someone already tried that.
But he didn't go inside.
Oh, well.
I just played around.
Test 1, 2, test 1, 2, test 1, 2, test 1, 2, test. Is it going down? Test 1, 2. Test. That's good.
It's okay?
For the moment.
Okay. So also we try to generate the similar format as Stanford parser, and which they have a slightly different relation, the relation name. And this is just try to compare the Stanford parser and RelEx, and so we can try to test the different bunches of examples. Yeah, so we can try to test some more complicated examples, like this one. The beautiful woman slowly gives her young baby a soft card. Then this is more complicated, as this has the two objects for one word. Yeah, so this example has more parses, which is more complicated, and then this is the RelEx output. So it gives two objects. One is the directed object and the indirect object. Also other subject and adjective modifier or verb modifier. So I can show you how the RelEx logic output look like. And so first, to run the RelEx logic, we have to start the OpenCog server.
Yeah, we couldn't get the HDMI.
Can you set the one?
She couldn't connect her own laptop. So I was trying to run it on the cousin.
It's too high. Can you make the microphone on the stand work?
Yeah, to run the RelEx logic, first we need to start the Cog server. Also, we need to start the RelEx server, which we use for the also in the RelEx folder. So now we can run the sentence in the scheme shell of the Cog server.
So now you're inside the scheme shell.
Yeah. Now just try to connect the server and enter the scheme shell. Now we can try to run the command R2L, then type the Okay, after you run the RelEx to logic command, then we can show all the output of RelEx to logic. Yeah, so we try to save the whole parse as a parse node into the atom space. So now we want to see how it look like. So we try to just show the inside of the parse node. Yeah, here I just try to show just the RelEx logic output, as we also store the link parser and link parser output and RelEx output into the atom space for the future use. Like we're going to use those functions for language generation, but now just try to show you the RelEx logic output. Here we go. So the example, this is the text sentence. Then we have the instance node of this, and as a general concept to connect with the inheritance link. Also, like this is a this is a text sentence. So this is also a sentence. Then we have also the inheritance link to connect this and sentence. I'm trying to show the same example showed for the link part. So here we have two parts now. The one was the first example, and the second must be the new one. To see the logic output, you can type the command like Pascal logic outputs. Then try to copy the parse node index. You don't need the truth value for this. Okay, so here we have more complex outputs, like the variation link, the woman.
The definite link is because it was the, right?
Yeah, the definite link means some specific woman, case of ugly frog, not a general woman.
If you had a beautiful woman kiss an ugly frog, then you wouldn't have a definite link. The definite link doesn't tell you that much, but it tells you somehow the speaker wanted to identify some particular.
Yeah, then we have the output like a beautiful woman, so means inheritance.
So look above there, like we have in the middle inheritance link between beautiful at CF blah 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 to beautiful. Now the bottom one there is the general concept of beautiful. The top one is the specific instance of beautifulness referenced in that sentence, and that's important for word sense disambiguation, because you don't necessarily know what meaning the word has in that particular sentence. And of course, if you had the very beautiful woman or the not very beautiful woman or whatever, then those links go to the specific instance rather than to the generic concept of beautiful. So we have more nodes and links than you might expect from such a simple sentence parsed into a semantic network. But it's necessary in order to handle the case where every word needs to be disambiguated, which is the most general case. Each word is an atom. Each word instance is an atom. For the instance of the wording that's, and if you're dealing with a different language where morphology is more important, each morpheme would be an atom. There's some work done on extending this to Hebrew and Amharic and Turkish, which have a agglutinative morphology, and then you need atoms for morpheme. So, yeah, there are fewer words.
Yeah, so here this evaluation link show the basic meaning of the sentence. Like the main meaning, it's a woman kissed frog. So as least being woman and frog being evaluated with the predicate or case.
Yeah, so I mean, in a basic predicate logic format, you have like kiss, parenthesis, woman, comma, frog, right? And that's basically what that is. It's predicate evaluation, except we have all those funny at symbols and numbers, because it's actually this instance of kissing occurred between this instance of woman and this instance of frog. And then other text in a sentence or other information not from language or whatever could tell you new information about those instances, which could include information that the woman wasn't actually a woman and the frog wasn't actually a frog, in spite of it having that name initially. But the stuff inside the quotes is the name associated to know it as an index in the system, but it's not actually parsed internally. So even though it was provisionally assigned the name frog at blah blah blah, it could still be decided that it wasn't actually a frog based on something else. There
could be another completely separate subsystem operating that has identified that toads are being processed for frogs.
Yeah. Or that the woman is actually a man in woman's clothing, or whatever it could be. You could have noticed through other senses.
So you have a code for each word as well as each context.
Each word instance, each sentence, each parse, and each interpretation of the sentence has a separate atom, actually. And potentially each interpretation, if you have multiple interpretations of a word instance in the context of word sense disambiguation, you would have multiple nodes for each interpretation of each word instance. So you can get a shitload of atoms just from one simple sentence. So if you use some technical term. Yeah.
Can you go into the word sense disambiguation? How is that done?
The only sense disambiguation that we've implemented in OpenCog so far is it's a variation on Reda Mahalsia's basically statistics-based word sense disambiguation, where we basically look at what senses have been most common for a word in a certain context and just add up probabilities from that. So we have a Google Summer of Code student this summer who is using PLN inference to do anaphor resolution. So to resolve it and her and him and what that means to. I think that Cody's writing can be generalized to do word sense disambiguation. It's kind of the same problem, right? Right now, we have PLN for anaphor resolution only. And we've just been doing some basic statistical stuff for word sense disambiguation.
Yeah. So the current system isn't perfect, but it can also pass some slightly complex sentence like an object clause. For example, this sentence is like this is a rejected clause which has a sub-sentence into the sentence like a soft hug that stops the crying. So we can also handle that.
Yeah, in general, I mean, with a rule-based system, you can handle anything if you put in enough rules, right? So a lot of work went into, I mean, Rodas, who's our linguist in Ethiopia, spent like 2 months doing the handling of comparatives. Like Ben, Ben is more insane than Cosmo is beautiful or something. And, just getting all the weird varieties of comparative sense is probably commas are still very annoying for the system. There are too many different meanings. I mean, ultimately, as with all rule-based engineering projects, it's kind of a hopeless and endless process to cover everything. But we've done this partly for some practical applications, and partly because we can now parse a lot of text and get a bunch of atoms in the atom space that we can play with for other purposes. But at some point, well before we get a human-level thinking machine, we've got to do away with all those rules and have them be learned by either just unsupervised corpus analysis or analysis of a corpus in conjunction with some kind of non-linguistic data. We've played with it a little bit, but that learning the linguistic rules is still sort of preliminary stage research, whereas the rule-based system does sort of what it's supposed to do. Yeah.
So it seems to be that an OpenCog you can plug and play various modules, right? That's the whole idea. They don't uniform it. So why, maybe a naive question, why develop your own parser as opposed to grabbing something off the shelf?
Well, so the link parser, which is the first stage in this pipeline, was developed by Slater and Temperley at Carnegie Mountain. So we didn't develop our own basic syntax parser. We took an existing syntax parser. Now, it ended up to have many shortcomings, so we made a huge amount of edits to its dictionary. But the thing is, we had a target, which is OpenCog's logic representation, and there is no parser that outputs that. So one way or the other, you can take a syntax parser, but then you have to do something to map its output into that. And then any syntax parser you pick has some strengths and some weaknesses, and there's a whole bunch of fiddling around that has to be done. I mean, in the end, we should be doing the parsing in the atom space as well, using more open. So I see this as sort of a scaffolding that lets us get some interesting data in this system. Yeah.
The last question, the last example is an example of context-sensitive acceptance. If you change the crying to, for instance, walking, that would change the meaning of the sentence. And what would the parser do with the last sentence?
Well, the goal of the syntax pipeline is to resolve only as much ambiguity as has to be done to get the structure of the parse right. And any other ambiguity is passed along to PLN or other mysterious processes. So we don't try to resolve the subtle meaning of the sentence in the syntax level.
So changing crying to walking wouldn't change the structure of the story?
Well, the thing is, the lint parser will output a bunch of parsers. And changing crying to walking will not output what is the set of syntactically correct parsers. It will merely output which of those is more semantically plausible in the context. And that ranking of different parsers according to semantic plausibility is to be done in the atom space based on PLN and other processes that have contextual information. It's not to be done in the early stages of the syntax pipeline. That way just leads complete madness. And if you try to deal with contextual meaning in your syntax pipeline, this can be even more of a horrible mess of rules than that.
Do you know the big performance of this was? Is this N-cubed or?
Oh, the link parser is an N-cubed algorithm. We also implemented link parsing using SAT, using some walk set, a Boolean satisfaction solver, which is exponential time, which is for long sense is much faster than the N-cubed parser. So I don't really think the order of complexity is not very important.
So, in terms of the performance, I guess you're so is this a supervised things that you're working with? Like,
No, this is a rule-based system. It's not supervised.
But I mean, in terms of to evaluate the requirements.
Well, you need to make a corpus of, well, depending on what you want to evaluate. The list parser, you want to evaluate RelEx, you want to evaluate RelEx to logic, you have to make a given marked up corpus to evaluate.
But in the example at the end there, it said 63%. I wasn't quite sure what that was based on.
I didn't see that. That was what it was. 63%. Well, we're not evaluating the accuracy of the norm.
Oh, yeah, that variation, that variation was counted by the it's kind of statistical from the link parser, like how often that link has been used. Then if that's a very common link, then we give a high confidence of the part.
Yeah, there's some statistical measurements that are done to rank the parsers, or which parse seems more likely or less likely based on statistical information. But we're not evaluating with the corpus. You could, but then you'd have to make a corpus for this part.
So when you talked about the census evaluation, I mean, I remember thinking about that, like, say, for instance, different census of, like, you take something simple like bank, you know, the financial bank versus the river bank.
Yeah, that kind is very easy.
But
The hard kind is the preposition disambiguation. Different meanings of or with or something.
right, or prepositional attachment or whatever.
Sure.
But in terms of the, like, inheritance things, that's more like, okay, it's like the young woman or whatever, it's more of a modifier of the, your say, for instance, it's a kind of woman, say, for instance, or something that's got these particular properties. They're sort of like two separate ideas, right? They're related, but they're different.
Well, yeah, you're right. I mean, if you have a node for the instance of a word in a sentence, there are many things that can be found out about that instance. I mean, one of those things is which word sense is it referred to. And then there's other information you can know about that instance also. So, I mean, the word sense is one. Word sense disambiguation is only one reason why you want to use separate node.